right? Okay. We got our folks online today? Nobody? We got Dan. Dan, a stalwart. Okay. So last time we got to going to this. B was Busenesque. I think that's how you spell it. Approximation. All sorts of fun French names and transport. Busenesque. We got Fourier. We've got all the French names in fluid mechanics like Ozoy and Couette. All fun stuff. Okay, so we got to this point, right? Rho is rho bar minus rho bar theta bar T minus T bar. Oh my goodness, we forgot to start with the curve. Better do that before we're going to have any hope of understanding this. Better ask help. Okay. Forgot the prayer. Can I get a volunteer for a prayer? You're going to make me say it. All right, Mark. I need someone with prayer.
Thank you that we can be here at school again to learn. We ask you to bless us and help us to understand the concept. We ask this in the name of Jesus Christ. Amen.
Amen. Thank you. Okay. So let's remind ourselves what we were doing. So we said, we wrote out these nasty multi-component equations, right? The big, gross, nasty stuff. And we said, like, we want to work with simplifications. And I said, you know, we did some simplifications in terms of Fourier's law and Fick's law and Newton's law of viscosity. We put those in. We said those are pretty good. But one other one we'd really like to use is incompressibility, right? Incompressibility makes our lives a lot easier when you don't have compressible flow. We said, but that's a problem because it's actually really common to have density gradients. And so, but that kind of incompressibility is different than when I've got, you know, a gas that's the volume and the temperature are exchanging, right? So that's a different, you know, kind of thing going on. You know, so if I have to write a whole PV2T equation of state and I have to solve that simultaneously, that's a whole mess, right? And Andrew testified to this. He was like, you know, I did an internship on CFD and I promised Busenesque is much easier, right? You know, and so he's seen the fruits of that and he's like, yeah, okay. So what did we do? So we said, well, let's write the density, the equation of state, okay? Because remember, when we wrote the big nasty thing, I think it was over here, I said you had to know rho as a function of pressure, temperature, and all the components, right? And I said, that's like a equation of state with all the mixing rules, okay? Which, you know, that's already made up anyway, right? Mixing rules are just made up thermo where people don't really know what to do. So they say we might as well just average it somehow, okay? And so we said, well, let's write down a Taylor series where we're going to say we're close to rho bar. How does that go? And we'll get the linear terms, okay? So that was from a Taylor series. And we said these guys here, this was the isobar compressibility, the volume expansion with temperature. And this one is the volume expansion with the change in concentration, okay? And so what we want to do now is go take this and plug it back in, okay? And we got to think, well, where are we going to put, you know, we plug this in everywhere. How does that work out, okay? And in the Busenesque approximation, we say something like, we make kind of a drastic simplification, and then we take it to be rho bar, this average density, everywhere except in the term that has to do with the gravitation and the buoyancy, right? So, you know, in the heat equation and all the other stuff, okay, density becomes a constant, okay? It's only in the Navier-Stokes equation in that one term that we let this go, okay? And so we're making kind of a big simplification there, but it allows us to write down a much simpler system, okay? And so this one I'm going to write up here for a binary as well, because we have to start drawing a line somewhere, right? I'm going to make this one non-reacting, so we're not going to think about reactions here, plus Busenesque approximation. And I'm going to stop writing Busenesque. I'm just going to put BA because, like, let's be honest, it's a pain to write. So this is what we get after that. We get a rho bar, dv dt. This is the momentum equation, minus grad. Now I'm questioning myself. But we're going to write it down. Let's make sure. Dynamic T plus grad squared v minus, and I'm going to go over here, rho bar, beta bar, T minus T bar, plus rho bar, beta bar, WA minus WA bar, close parentheses G. Okay, we'll talk about these just a second. dt, d little t is equal to alpha grad squared t. The WA dt is equal to DAV grad squared WA. And then we have a couple other little things here. We have the total continuity equation, del dot V is equal to 0. And we should write what the dynamic pressure is to just remind ourselves, grad P minus rho bar G. Okay? And so where there was a rho C sub P before, for instance, in the thermal diffusivity, that's now a rho bar. Okay? I think we have all of the pieces in there.
In the density over there, it doesn't have the average density, or did you distribute it?
So the average density, that's where it goes. The average density we pull out and we put into this dynamic P. Okay. So now we have, so I could have written grad P, and then that's what I was trying to remember as I was writing it. I put that rho G here, but instead we just pull it out here and plot it. Okay.
Question. What did you say that the beta and the zeta are?
Yeah, this is the volume expansion coefficient. Okay, so this is sometimes called the isobaric thermal expansivity. Okay, and I don't know if this one has a kind of a fancy name, but it's equivalent for concentrations. So how much does the volume change as a function of concentration? Okay, so my comments on this equation are, so think about what we've assumed here. So we've assumed this, non-reacting and binary. We've assumed the Boussinesq approximation. We've assumed, Fourier's law, Fick's law, and Newton's law of viscosity. We've assumed constant K and C sub P and DAB. Okay, so that would be like a dilute solution when we did this, right? And K and C sub P means our temperature gradient's not so big, or that we're gonna have to worry about the changing heat capacity as a function of temperature, right? So it's important to recognize these things in these equations, because if you want to sort of go back, so suppose you had a homework problem or something where you had to, or a problem in real life in your research where you had to go, well, I can assume all of this, but I can't assume a constant diffusivity. You have to remember to go back to the del dot DAV, C DAV, etc. Right? Grad WA. And how that changes this side, etc. Right? So you have to just make sure that you know how to do those steps. That's why we write the general equations, not because you ever want to start there completely, but so that you can recognize, how to go back on any one of them, right? Back to their original cases, and know what you should be worried about if some physical thing is in your system, what you should check next, right? If it's not described. Okay, so are we okay with this guy? Does this make sense? Okay, so that puts us to C, which is dimensional analysis. As you can tell, is one of my favorite parts of transport. Okay, so I don't want to go too deep because I'd rather spend some of our time today doing some examples. All right, one example in particular, but I want to motivate the main point of this dimensional analysis is to get the Grashof number, okay, and to talk about what that means, okay, so we can understand that, right? So let's just think about these cases we talked about before. So let's think about a case where I've got EAB, rho R, U. I've got two parallel permeable membranes, okay? And I'm going to say up here I have WA1, down here I have WA0. And let's call A the solute. Say it's not super concentrated, right? And B I'll call the solvent. And let's say that WA1 is greater than WA0, right? So that's going down. And let's say then that rho 1 is greater than rho 0. Is that right? So rho 1 is greater. That means I'm going to want to have a density that's going to flow downwards, right? Okay. So because of that concentration, I get this density difference. All right. And I think we're going to call that distance. All right. And so we can take these equations that I just wrote up here. We're going to neglect the temperature equation. Okay. So it turns out that we can do this with temperature, or we can do this with the mass transfer, or we can do it with both. But doing it with both is going to give us, Grashof equation for the one and for the other. So I'm just going to pick one for this example. So I'm just going to do the mass transfer. So we'll just write that up right here again. Rho dV dt is equal to minus grad P plus mu grad squared V minus rho G zeta with the bar on the row. Don't forget the bar. WA minus WA bar. And then dWA dt equal to DAB grad squared WA. Okay. So now we need to pick scales, right? That's how we do this. So we're going to pick a length scale. This is the sort of key part when you do dimensional analysis. The rest is the same every time. So the length scale we'll pick to be L. Okay. And now we need to pick a time scale. And that's the thing that's maybe not obvious here. I don't have something shearing, right? So notice when I have forced convection, that's what fixes the time scale. And that's really what's different about these problems. If you go back and think about mass transfer, is there's different time scales going on because there's different mechanisms of how full flow is happening. So in free convection, the time scale that we're going to pick is, we can pick either the diffusion time scale that comes from this one. So DAB over the length square. That's going to give us the diffusive time scale. We're actually interested in a momentum time scale. We just don't know what it's going to be. So one of the other ones that's kind of interesting to pick, and it's not right. It's just another one to pick, and it'll turn out to be useful to pick here, is to pick the momentum diffusion time scale. So just like we had, diffusion, and we could say this is a length squared per time. If we write down nu, right, that's a length squared per time, the kinematic viscosity. So if that's a length squared per time, then if I write L squared over nu, that's going to give me a time scale for momentum diffusion. Okay. So then I could write down, say, a velocity scale. So U should then be, if that's the time, and a length per time would be, let's see, a length per time, did I write that down wrong? Oh, that's time is in the bottom here. So length per time would be nu over L, right? So I flip it upside down and get 1 over time, and I multiply by a length. That gives me a length per time. So that would be a velocity scale. Okay, it's not, there isn't any U in there, but that's just a scale for the velocity. Okay, and now when we have the fluid mechanics equation, we need the pressure scale. So a pressure scale goes like rho u squared, if you remember, rho bar. Oh, watch the rho. So rho bar u squared. And so I just put a rho bar and square that guy there. I get nu divided by L squared. Okay, so I think that's all I need. So now I do the process we've done before lots of times, okay, where I go through and make substitutions for the variables in here, right? I define the x, and that gives me the gradient. I define pressures, etc. Okay, I'm just going to skip that step, leave it as an exercise for you to do, okay, to show you, and I'm going to write up what the final thing is so we can talk about what that means. That skips us here, and I think I'll erase real quick. I'll write up what you get. So you get dV dt is equal to minus grad dynamic P. Where'd it go? Plus grad squared V minus G zeta WA1 minus WA0 L cubed divided by nu squared, and then G WA minus WA bar and a tilt on the bar. And then you get D WA tilde dt tilde is equal to DAB divided by nu grad squared WA. Okay, so maybe a couple of things to point out. So got tildes all over the place. So, you know, these tildes come from their sort of normal definitions, you might think. This G tilde, this is just the G vector divided by G. So I could pull out a G here. So this is really going to look like -1, but in vector, in whichever direction the Z direction is, okay? That's really just a unit vector. And then the WA, you do, you know, we can maybe write that over here. You're going to write that WA tilde is going to equal WA minus WA naught divided by WA1 minus WA naught. So that's where part of this comes out here, okay? And then this WA bar tilde is the same thing, but I just put a bar, right, for the average WA. So this one's the function one, right, and that one's just the average value in the system, okay? So we get two dimensionless numbers out of this. We get this one right here, and we get this one right here. Well, this one here is called the Grashof number. Okay, and I guess Grashov, I don't know. Maybe if he's Russian, I don't know. You can tell me. I don't speak that language. Okay, and this is buoyancy. Oh, I always want to do that. Buoyancy divided by viscous forces. Okay, this one we've seen before. This is the Schmidt number, which is equal, it's actually 1 over the Schmidt number. Because the Schmidt number is equal to nu over DAB. Okay? And the Schmidt number, I think, hopefully has a pretty obvious interpretation by now. This is momentum diffusion divided by mass diffusion. Okay? So let's think about the Grashof number for a minute. So the Grashof number, right, it's in front of the buoyancy term. That makes sense. Okay? And by picking the momentum diffusion scale as my time scale, what I said is that, this is a viscous time scale over here. So I don't have I don't have this external flow that's giving me an inertial force. All I have is free convection, okay, that gives rise to flow, all right? And then that flow has a viscous scale. So I don't have an inertial scale, so I don't have a Reynolds number, okay? So if I have mixed convection where I have both forced and free convection, then I can have that, okay? So I hope maybe that makes a little bit of sense there. So let me see if there's any more comments I had about this, and then okay, so the one other comment I would say, so if I do this for temperature, I also get a Grashof number. So the Grashof number for temperature looks like this. I get G beta bar T1 minus T0 length cubed divided by mu squared. Okay, so you can see the part that changed is the part that is the beta delta T, whereas up here it's the zeta delta W. Okay, and you can pick a different way to write down so for instance, if you took the other time scale that I said, suppose you pick the diffusion time scale, okay, then you're going to get something different. It's going to look a little different up here, but you're not going to just get these two numbers, but the equations will say the same stuff. You're allowed to mix and match, right? I just think this one happens to show nicely with this particular problem. So if you pick the diffusion time scale, you'll get like a 1 here, and then you're going to get, time scales with this. So you're going to get like Peckley numbers and stuff. There's a Peckley numbers or maybe a Reynolds number that comes from that scale that's different. Okay. So that's what goes on with the dimensional analysis. You can see there's a table in your book that goes through like all the different cases you can do, which is for the temperature one, table 11.5-1. And there's also more in equation 19.5-8 through 19.5-11. Okay, so those are some things to look up in your book if you want to sort of review this for yourself a little more. Okay, questions about the dimensional analysis before we work on the example problem? Riveting stuff. What do you think, Christina? Makes sense? We've seen it, kind of done this before, right? Well, guys got big weekend plans, running an experiment, going on a date, studying transport, getting ready for your exams. You're done with all your other exams for your other classes, right? That's kind of good about me, like waiting, Then it's just my exam. You don't have to worry about anything else. I can make you study for mine.
You just have to decide if it's a 3-hour or unlimited.
No, I'll tell you. I have to scout. I'm thinking it's going to be 3 hours. That's my thinking. I think that's mostly merciful. But I want to make sure as I kind of pick the problem that I don't want to torture you, right? So, but that's what I'm thinking. That's what I'd like to do. So, we'll see. That's my weekend. I get to write a test. So fun. So fun. My favorite part. Favorite test. Okay. Tests are the worst. I'd rather take a test than write a test. You could write an easy test. That'd be pretty quick for you. No, easy tests aren't that like so. Okay, I could write like a trivial test, like something that's just stupid. Yeah, okay. But an easy test is not that easy to write. Trivial's okay. Trivial. Here's your test. How's class going? Describe transport to me, you know? I don't know. I mean, you don't really want me to do that. You want to learn. You're here to learn, right? Like you want a good graduate education. And so you want to know, like, did I get something? Or did I miss? Like at this point, the grades aren't to like get you, right? Like you're all going to get A's and B's if you turn in all the homework and you take the exam, you know, like it's, I mean, and as you basically studied, right? Like you all know how to do that kind of work by now. So like, you know, we're not doing a test to like get you or to sort you. It's for the learning, right? Like so that you take a chance and review and you put that stuff in your head and you go back and make sure you have all the questions down. And a little bit of stress, right? Like that pushes us to do stuff, right? There has to be some stakes. If I say like, you know, well, you can just do whatever, and then there's no stakes to the exam, well, you don't work as hard, right? Like we're all lazy, right? Like we have to have something pushing us, you know? If I didn't have teacher evaluations, who knows if I'd show up, right? No, that's not true, but you get the idea. Okay, so let's talk about, okay, so let's just step back. So with the Plisk approximation, right, we can now do free convection. We can now do these density-driven problems, okay? And we're going to try and contrast this with forced convection. So in the forced convection, I think we did a similar kind of two-dimensional problem. And we'll start with that one here. We're going to do, or I call this D. I changed it in my notes. So I'll call this 1. So this will be free convection. I lied. I'm going to do this other one first. This one, we finish one. I want to finish this one. Okay. Between. This one is not in your book. The one they do in your book is on a single vertical plate. Okay. And I kind of hate that problem because it turns into a PDE. And it ends up being the same equations as the boundary layer equations. We haven't done that yet. I don't know why they do that problem before they do boundary layers. Maybe they do it in BSL because they assume you're going through the book linearly. Whereas Bill organized his notes like we're doing, you know, like we're going 1, 4, or, you know, 1, 5, 9, or whatever, right? We're jumping like that. And so maybe they're assuming we've done boundary layers. But anyway, I haven't done boundary layers, so I'll like it that it's there. Okay. So here's this problem. So I have T equals T1 on one side. I'm going to do temperatures for this one. T equals T2 on the other side. Alpha mu. There's a distance of 2h. I did it in temperatures because the book that I was looking at did it in temperatures. Probably should have translated it to mass, but it's easier to think about, I think, the temperature in this case. So this will be 0, this will be plus h, this will be minus h. So I have these two parallel plates. One's heated, one's cooled, or one's at room temperature and one's hot, right? And so I'm going to say that T2 is greater than T1. So if you think about what's going on here, right? So if the one side's hot, the other side's not hot, you'd expect that the one side's going to cause flow to go up, the other side's going to cause flow to come down. And like Andrew's doing a circly thing with his hand, right? So if I close the top and bottom eventually, you know, flow can't go anywhere. I'm going to get some circular flow around in between these parallel plates. So that's the thing we expect to get. So our equations are temperature here, dt, d little t is equal to alpha grad squared t. Then I get rho dv dt equal to minus grad p plus mu grad squared v minus rho g beta t minus t bar. Okay. Okay. So the first thing to do here is to solve for the temperature distribution. Okay. So if you look, we don't know what the velocities look like, okay, but we can solve for the temperature distribution. This doesn't have anything else in it that's coupled. So unlike so if you think about the forced convection problem, what we did there was solve the velocity problem first, then plug that into the concentration case. And this one we do the opposite, right? We're solving the, you know, concentration or temperature problem first, then we're plugging that in and getting the velocity thing out. In this case, we're going to get a simple solution here, which will allow us to solve this one here. Okay. If this one gets kind of messy, then it's going to mess this up because this will have nastiness in it, right? Or if this is a complicated geometry, something could get messed up. So let's solve this problem first. Well, this problem, if you think about it, so if we assume, let's assume steady as well, because who wants to not do that? Okay, unless we have to. Okay, so steady state, we're going to get grad squared t equals 0. Right? So if I get grad squared t equals 0, that means, and I only have this direction here, let me put some x and y axes on here. I'm going to call this one y and that one z. So this means the only gradient I have is d2t dy squared equals 0. And I have constant temperature boundary conditions, T2 over here, T1 over here. We have solved this a lot of times. Like if that would be the trivial exam problem, right? Like solve the temperature distribution here. Okay. And so this one I get out, T is equal to, and I'm just going to skip all the way ahead, T2 minus T1 divided by 2H and Y plus T1 plus T2 divided by 2. Okay, so I get a linear temperature distribution, right? That's just between T2 and T1. Okay, happy with that. So now I got to take this and plug this back in here and solve for the velocity distribution. Okay, so let's assume that I get laminar flow, right? That this temperature isn't so fast that I get turbulent flow. So if I have laminar flow, I'm gonna then assume that it's unidirectional. Okay, and with that that means I have Bz as a function of y only, right? So I'm gonna have velocities in z, but it's only gonna change in the y direction. Okay, so that means I can write this guy a lot simpler. If you remember, for unidirectional flow, that implies that the whole left-hand side here is 0, right? And so I end up with, I'll come over here, we go on the trace.
The unidirectional makes the left-hand side?
Yes. Yes. Unidirectional and steady. So remember the, well, I guess we said steady. Remember there's the little d v dt and then the v dot grad v. And the v dot grad v was 0 because of unidirectional, right? Because that meant that the velocity and the gradients of the velocity are fine, right? And so v dot grad v, like their 90-degree angle, that's 0, right? Okay. So I can write just the vz of y component, and this looks like minus dp dz plus mu dvz dy, second derivatives, plus rho g theta t minus t bar. Okay, so this looks just like what we simplify to when we get Couette flow or Poiseuille flow, right? In Couette flow, even that guy is 0, right? In Poiseuille flow, that guy has something because we have pressure driving the flow, okay? And so now we have this extra term out here, which is our free convection term, where we've got density gradients driving, okay? And so we could solve this problem where you have both forced convection and free convection. So if you put a pressure gradient along that, so say the ends aren't capped, but you put a pressure at one end and another pressure at another end, you'd have a term here, okay? And then you have to solve it out. That might be like a good exam question, right? So like do that instead of what I'm gonna do. What I'm gonna do is assume the ends are capped, since you don't have a pressure gradient. So I'm gonna assume that term is 0, okay? And so now all I wanna solve is this guy here, right? With these pieces. So what I need to do then is put in T minus T bar. Okay, well, what's T bar? Well, T bar, the average temperature, T1 plus T2 by 2, right? So what I do, T minus T bar is just going to be this piece right here. That's really convenient, okay? So now I have 0 is equal to mu dvz dy squared plus rho g beta, and then I have T2 minus T1 divided by 2H multiplied by 1. Okay? I missed a minus sign somewhere. Reason that's plus, that's good. No, I'm okay. I'm good. Okay. So from here, now we have to solve this guy. Okay, and then we'll have our final answer. So I'm going to write this as delta t going forward to save myself a tree. Yes.
Over there, you wrote minus rho g.
Yes. Yes. So this g is a vector, which is 0, 0, minus g. Yes. I was thinking about that when I stood up. So thanks for bringing that up. Yep. Okay. So now let's solve this. So I get e squared vz dy squared. Move that one to the other side. So I get minus rho g beta delta t divided by 2 mu h y. Okay. This one, separate and integrate. Let's do that. So I'm going to integrate this one once. Let's do that. dvz dy. And I'm going to get minus rho g beta delta t divided by, and then I'm going to have y squared. So I get a 2 down here. So now I have 4 mu h plus a constant. And then I do another one, right? And now I get Vz. Oh, right, as a y. I'll just put this as minus rho g beta delta t divided by. Now I do this, it goes to the third power when I do the next integral, right? So I get a 3 down here. So 3 times 4 is 12. So 12 mu h. And then y cubed plus c1y plus c2. Okay? And now I need velocity boundary conditions. So what are my velocity boundary conditions? Well, I can say that vz at plus h is equal to 0 from no slip, right? And I can say that vz at minus h is equal to 0 from no slip. So then I can plug plus h and minus h into both of those guys. So let me write that out. Minus rho g beta delta t over 12 mu h. Plus h gives me h cubed plus c1 h plus c2. And then I'm going to put that one down here. I'll say that equals minus rho g beta delta t 12 mu h. Now I get a minus h cubed. The minus will stay, right? So this should become a plus h cubed. And then this one should be also minus c1h plus c2. Okay? So then to find the boundary, to solve this, this is just algebra here, right? So I can subtract them and solve for c1, and I can add them and solve for c2. So that's pretty clear. If I add them, that I get c2 equals 0, right? If I subtract them, I get c1 is equal to rho g beta h delta t divided by 12 mu. Okay? And so then I can plug that back in and get the answer. And for lack of time, I'm just going to write it, simplified version. I get the following. This becomes Vz is equal to rho g beta h squared delta t divided by 12 mu. And I get a y over h minus y cubed over h. Okay? So that's the final answer. So that's kind of interesting. It's a cubic. So let's think about just what that means. So if I make my plot here, and I make this both temperature and velocity, okay? I'm going to make this one my y-axis. So the temperatures, right, if this is my wall over here, this is my wall over here, I had a temperature gradient. That's not like very symmetric about it. Let's fix that at least a little bit. Okay, so I have a linear temperature gradient like that, right? And what happens? So if I plot this equation, that's going to give me a cubic that looks like this, right? Where over here I have velocities that go up on this side and velocities that go down over here, okay? And then this line right there, right? That's at 0 here because I have to have the flow rate add up to be exactly 0 if I close the top and the bottom, okay? If I were to have done something like impose a pressure gradient, what you'll see is that this will shift this a little bit, okay? Because now the way the pressure flows is going to cause this to be, off kilter, okay? So we'll leave it at that. Yes.
Y cubed over H, should that be H cubed?
Oh, H cubed, yeah. Thank you. Or else dimensional consistent. Okay, so there we go. We got that example done. I'm not going to give you an example. It's in your book. What example was it? Tell you what the other one was. It was. All my pages are out of order. The other example was in section 11.4, example 11.4-5. That was not this one. That was the single. Gives you a PDE. Okay, we did it. We really will have an exam review on Monday. I promise. And we'll do an exam on Wednesday. I'll put the exam on Monday is what I'm going to do. You can, we won't have class Wednesday. You can. Okay. I'll tell you all the format of the exam on Monday.